Let's take a look at the Free State 2025 Prelim Paper 1. Multiple choice question 1.1. When a book lies on a table, it does not move because. So what I'm going to do is I'm going to draw a free body diagram of the forces acting on the book when it's on the table. So you have the force of gravity and you have the normal force. Now, it's not moving, so it means that the normal force is equal to the force of gravity. Those two forces are in equilibrium, and so the answer we are going to choose is C. Option A is not entirely, it is correct, it shows an action-reaction force, but it doesn't explain why the book is not moving. Question 1.2, a maximum force of 8 newtons is exerted on the 6 kilogram block, which is at rest and just about to move. Which one of the following will increase the frictional force experienced by the block? So remember, friction is equal to mu s times Fn. We're not going to be able to change mu s. So the only way we can increase friction is if we increase Fn. The way to increase Fn would be to make the block heavier. So how can we make the block heavier? By placing another block on top of it. So the answer there is C. Question 1.3, the acceleration due to gravity on the moon is g. Which one of the following represents the acceleration due to gravity on a planet that is 3 times the mass and 1/3 the radius? So we can simply say g is equal to g, and then the mass is 3 times, so 3m over 1/3 r, and then all squared. We can now simplify. You're going to get 3gm over 1 over 9 r squared. 3 divided by 1 over 9 is 27. So 27 gm over r squared, or in other words 27g. The answer here is B. Question 1.4, a body falls freely in the absence of air resistance. Which physical quantity of the body is equal to the rate of change of momentum? Now, we can write that F net is equal to delta P divided by delta T. Now, as this object is falling, the only force acting on it is the force of gravity, and Fg is equal to ma. So ma is equal to delta P divided by delta T. Now, we can then simplify. ma we can rewrite as mg because it's accelerating with 9.8. That's equal to delta P over delta T. mg is the weight. So the weight is equal to the rate of change in momentum, so the answer is B. Question 1.5, a ball is dropped from a learner's hand to the ground. Which graph represents the kinetic energy? So EK is equal to half mv squared. Since half and m are constants, EK is directly proportional to v squared. V squared is a parabolic function, so we are looking for half a parabola. The answer 1.5 is A. 1.6, an astronomer on Earth observes light with a wavelength lambda originating from a distant galaxy moving away from Earth. That is important. The wavelength observed by the astronomer will be, if it's moving away from Earth, it means it's going to be red shifted. Now, if we look at our colors, R, O, Y, G, B, I, V, red shifted means it's shifting towards the higher lambda end of the spectrum. So the answer here is going to be A. If something is moving toward us, it's going to be blue shifted. Here it's red shifted means it's moving away, it's moving toward a higher wavelength. Question 1.7, consider the electric field patterns around the charged particles Q, R, and S as shown in the diagram. What are the respective charges? So Q is definitely going to be a positive charge because the arrows are moving away. R is going to be a negative charge, and S is also going to be a negative charge. But because S has more arrows, it's going to be of a higher magnitude. So the answer that we're going to choose here is going to be C. Question 1.8. The circuit diagram below has two identical resistors, R1 and R2, and a battery with a potential difference of V. What is the potential difference across the resistor with resistance R2? Now, one way to calculate it is if we look at the total resistance. The total resistance is going to equal R1 plus R2. Then we can use the formula V is equal to I times R to calculate the voltage across R2. So the voltage across R2 is going to equal the current that's going through R2 multiplied by R2. Now to calculate the current that's going through R2, that's reading the total current, we can say that I is equal to V over R. So I total is equal to V total divided by R total. R total is going to be, so V over R1 plus R2. We can now take this and substitute it there. So VR2 is equal to V over R1 plus R2 multiplied by R2. Now if we look at our options, because this is multiplication, we can switch these. And so we can have V is equal to R2 over R1 plus R2 times V. The answer is going to be D. Question 1.9, the difference between a DC and an AC generator is that a DC generator uses brushes for commutation, while an AC generator uses slip rings. Okay, it doesn't use brushes for commutation. It uses a split ring commutator. It produces a unidirectional current where an AC generator produces or generates an alternating current. That is correct. Question 1.10. The number of photoelectrons emitted by an incident light of frequency f, which is higher than the threshold frequency, is proportional to what? So the number of photoelectrons being emitted is proportional to the intensity of the light. Remember, if you have a light of a higher intensity, you are going to have more photoelectrons emitted. If you are changing the frequency, you are going to then be changing the kinetic energy. Let's take a look at question 2. A 73 kilogram man is at the bottom of a 34 meter deep hole. He is pulled vertically upward from rest. The tension in the rope is 780 meters. Question 2.2, draw a free body diagram showing the forces acting on the man. So when that man is being pulled up, he's going to experience a tension force and is going to experience a force of gravity. Question 2.3, calculate the magnitude of the man's weight. Now, to calculate the weight, so 2.3, we can say that Fg is equal to mass times gravity. The mass is 73 and gravity is 9.8. That's giving us a value of 715.4 newtons. Question 2.4, calculate the time taken to pull the man out of the hole from position A to position B. Now here we can use an equation of motion. Now, if you look at the mark scheme, it's worth 5 marks. So probably going to need to do more than equation of motion substitution. So what information do we know? Well, we know the VI is 0. We know that he's traveling, so let's say delta Y, because he's moving in a Y direction, it's 34 meters upward. And I think that's about it. However, because we got a free body diagram, we can use Fnet. We can say Fnet is equal to MA. I'm choosing up as positive here. So the tension minus the weight is equal to MA. Tension is 780 minus 715.4 is equal to 73 times acceleration. The acceleration is then equal to 0.88. So now we know the acceleration is 0.88. We can use an equation of motion to calculate the time. We can say that delta y is equal to vi delta t plus half a delta t squared. So 34, again choosing up as positive, is equal to 0 plus half into 0.88 and then t squared. T is then equal to 8.77 seconds. Question 2.5, will the tension in the rope be greater than when the man is at rest or when the man is pulled upward? Explain your answer. Now here, this is quite similar to a lift problem. So let's draw two different free body diagrams, one when the man is at rest and one when he's accelerating. So when he's at rest, he's going to have two forces. Well, he's going to have force of gravity and he's going to have tension. But he's not being pulled up yet. And then when he's moving up, there's tension and there's force of gravity, but this time there's acceleration upward. So here we can say F net is equal to ma. Since he's not moving, the acceleration is 0. So t minus w is equal to 0, t is equal to w. But when he's accelerating upward, he's going to have F net equal ma. So t minus w is equal to ma. That means t is equal to ma plus w. The tension is actually going to be greater when he's being pulled up. It's going to be the weight and the mass times acceleration. So the tension is going to be greater when the man is being pulled upward. Question 8.3, vertical projectile motion. Ball A is dropped vertically downward from the top of a 25-meter high building. 1 second later, another ball B is thrown vertically downward from the same height with a speed of 30 meters per second. Now, this setup is quite similar to another video that I've done. I will link that in the top right corner. Ignore the effects of air friction. Question 3.2, use equations of motion to calculate the time it takes for ball A to travel 12.5 meters above the ground. So question 3.2.1, if I'm choosing down as positive, the delta y for ball A is going to be 25 minus 12.5, which is equal to 12.5. Now here they chose 12.5 because even if you didn't do the subtraction, you still get the answer correct. Since ball A is dropped, we know the VI is going to be 0, and we know that acceleration is 9.8 downward. Now, if we want to calculate the time, we can use the formula delta y is equal to VI delta t plus half a delta t squared. So 12.5 is equal to 0 plus half into 9.8 and t squared. T is then equal to 1.597 seconds. Let's take a look at question 3.2.2. Calculate the time it takes for ball B to pass ball A. Now this is worth 6 marks. So definitely going to involve multiple calculations here. So for ball A, the information that I know is, well, let's call the time for A, let's call it t. Then the delta y for A, I'm not sure what it is. Right? I don't know how far it's going to have traveled. I know the acceleration is 9.8 down, and I know the VI is 0. For ball B, I know the time for ball B is going to be the time for ball A minus 1. And the reason why it's minus 1 is because ball B was thrown a second later. So it's traveling for a time that is 1 second less than ball A. The delta y for B, I don't know what it is. The acceleration is also 9.8 down, but its VI is going to be 30 downward. It's thrown down. So for ball A, I can say delta y for A is equal to VI delta t plus half a delta t squared. So the delta y for A is going to equal half into 9.8. Remember, this is 0. And then t squared. I can then simplify. The delta y for A is 4.9 t squared. Now for B, the delta y for B is going to equal 30. So I'm using the same formula, VIT plus half AT squared. So 30 into t minus 1 plus half into 9,8 and then t minus 1 all squared. I can now simplify. I'll get delta y for B is going to equal 30t minus 30, then plus 9, well, that's 4,9 into t minus 1 all squared. Now, here's the thing. When A and B pass one another, they are going to have traveled, or they are going to be at the same height. So I can equate these two. I can say delta y for A is equal to delta y for B. So 4.9 t squared is equal to 30t minus 30 plus 4.9 t squared. Now I'm expanding this, and that's going to be minus 9.8 t plus 4.9. Now I can simplify. 25.1 is equal to 20.2 t. T is equal to 1.24 seconds. Now, because the question is a bit vague, the question isn't asking, well, the question is asking the time it takes ball B to pass ball A. The time that we've calculated here is the time that ball A is in the air for. But, so this is, so for ball A. Now, ball B was in the air for 1 second less. So the time for B is going to be 0.24 seconds for ball B. I'm just going to put both because the question is a bit vague and there's no memo, and so we're just going off what I think the answers should be. Question 3.2.3, calculate the speed of ball B when it reaches the ground. So this is a simple one. I can use the formula Vf squared is equal to Vi squared plus 2a delta y. So Vf squared is equal to 30 squared plus 2 times 9.8, and when it hits the ground it would have traveled 25 meters. So Vf is equal to 37.28 meters per second. They're asking for speed, and so we don't need to give a direction. Question 3.3. On the same set of axes, sketch the position time graph of ball A and ball B while they are in free fall. Label the graphs A and B respectively. So I'm going to draw my axis here. That's going to be position. That's the ground, 0 and 25 meters. So this is going to be the 1 second mark, and this is going to be the 1.24 second mark. Now ball A is thrown at time 0 from 25 meters, and it goes down and it hits the ground like so. Ball B is thrown at 25 meters but 1 second later, so here. So that's going to be the starting point, and it is going to pass ball A at 1.24 seconds. So the graph should go like this and cut through here. And because it's thrown, it will hit the ground at an earlier time. So this is going to be A and that's going to be B. They didn't ask for us to label the time at which they hit the ground, so that's fine, that's sufficient. Let's take a look at question 4. A car of mass 1,200 kilograms is moving at a speed of 25 meters per second east. Crashes at the back of a truck at that mass and that speed, and they give us the velocity after the collision. Question 4.2, calculate the velocity of the truck after the collision. So 4.2, I want to say the sum of the initial momentum is equal to the sum of the final momentum. So choosing east as positive, I'm going to say 1,200 times 25 plus 6,000 times 15 is equal to 1,200 times 16 plus 6,000 V. I then solve for V, and that's equal to 16.8 meters per second and east. Question 4.3, calculate the mechanical energy lost during the car-truck collision. Now remember, mechanical energy is equal to EP plus EK. There is no change in the heights, so we can simply calculate the kinetic energy, and that's going to be the mechanical energy. So we'll calculate the kinetic energy initial. That's going to equal half of 1,200 times 25 squared plus half of 6,000 times 15 squared. And that gives us an initial kinetic energy of 1.05 times 10 to the 6 joules. Now we'll calculate the sum of the kinetic energy final. That's equal to half of 1200 times 16 squared plus half of 6000 times 16.8 squared. And that's equal to 1.00032 times 10 to the 6 joules. So there's definitely some energy that was lost. So the kinetic energy lost is going to equal the final minus the initial, which is 49680 joules, and this is also going to be the mechanical energy lost. Question 4.4, explain why mechanical energy is lost. Well, mechanical energy is lost because the collision was inelastic. So the kinetic energy was not conserved. Question 5 reads, an 8 kilogram steel ball initially at rest is pulled upward by an electric motor with a constant applied force of 45 newtons. The ball moves at constant speed in each of the sections x, y, and yz along a rough inclined slope as shown below. Each section is 4 meters long and exerts a different frictional force on the steel ball as it moves up the incline. The incline makes an angle of 25 degrees with the horizontal. They give us a diagram here, and the graph is of kinetic energy versus distance. Question 5.2, use a suitable formula to show the physical quantity represented by the slope of the graph. Now, to work this out, we're going to look at the formula W net is equal to delta EK. Now, W net can be rewritten as F net times delta X, and that's going to equal delta EK. Now, if we rearrange this, we'll get F net is equal to delta EK over delta X. If you look at what we have on our y-axis, we have kinetic energy, so that's going to be delta Y over delta X, and that's the gradient. So F net is our gradient. Question 5.3, calculate the net force experienced by the steel ball as it moves from Y to Z. Now, these questions, 5.3.1, 5.3.2, 5.3.3, are quite problematic because they tell us that this object is being moved up at a constant speed. Now, if it's being moved up at a constant speed, F net is going to equal ma. Constant speed means a is equal to 0. That means F net is going to equal 0. But we can clearly see that from Y to Z, there's Y, there's Z, we can calculate the gradient, and the gradient will give us some value. So that is why question 5.3.2, 5.3.3, these questions were removed. Though we could calculate it if we assume that it's not moving up at a constant speed, but that's not part of the question. So if you do want that, please let me know, and then I can come back and take a look at that. Then question 5.4, which region X, Y, or YZ has the largest frictional force? Explain your answer. Now, again, this question can be answered, but in terms of physics, like the physics properties and principles, it's not really going to work because F net is 0. But let's assume, just like hypothetically, let's assume that it's not moving up at a constant speed. How would we answer this question? So if we look at the gradient, right, we can say that the gradient here is lower than the gradient there. So it means that the F net from X to Y is less than the F net from Y to Z. Now remember, F net is equal to ma, and if there's forces being applied on this object, there's going to be the force applied, there's going to be gravity parallel, and there's going to be friction. Now, if the F net is getting lower, the only reason why F net would be low is if friction is high. That's because the force applied, they tell us, is constant. The W parallel is going to be constant. So since the F net is low between X to Y, it means the friction is higher here. Again, but this question is a bit of a mess, and they're probably going to discuss on how they're going to do the adjustments. Let's take a look at question 6. Two identical aircraft, A and B, each producing a sound wave with a frequency of 600 Hz, start moving at the same time in opposite directions away from the airport tower. So to give us a diagram, they tell us a listener sitting in the tower measures a 30 Hz decrease from the actual frequency of aircraft A, while the frequency measured for aircraft B is 450 Hz. Okay. Assume the speed of sound is 340 meters per second. Name the phenomenon. Of course, we know that's a Doppler effect. How does the frequency heard by the pilot in aircraft A compare to the actual frequency of sound produced by the aircraft? It's going to be the same, right? And why is it going to be the same? It's going to be the same because the pilot is inside the aircraft. It's kind of like the scenario where like an ambulance driver is inside the ambulance. He's hearing, or the ambulance driver is going to hear the actual frequency, the frequency of the source. There's no distortion because there's no relative motion between the listener and the source. And let's look at question 6.4. Calculate the distance d between the two aircrafts after they moved in opposite directions at a constant velocity for 60 seconds. So I'm going to make a note of the things that I know. So I know the velocity of the listener, so VL is going to equal 0. The tower is not moving. I know V is 340, so the velocity of sound in air. Then for object A, or for plane A, I know the frequency of the listener is going to equal, they tell us that the frequency of the source is 600. So frequency of the listener for A is going to be 600 minus 30. They tell us it there is a 30 Hz decrease, so that's 570. Then the velocity of A I don't know, and I can use the formula. FL is equal to V plus minus VL over V plus minus VS times FS. FL is 570, that's equal to, now because it's moving away, I'm going to have a small top and a big bottom, so 340 over 340 plus VA multiplied by 600. VA is therefore equal to 17.89 meters per second, and it's moving to the left. Now if I take a look at B, for B I know the FL is equal to 450, right? Because they've given that to us. So I can use the formula. FL is equal to V plus minus VL over V plus minus VS times FS. Now here again it's moving away, so small top, big bottom. 450 is equal to 340 over 340 plus VB multiplied by 600. VB is equal to 113.33 meters per second, and it's moving to the right. Now they tell us that it's moving at a constant velocity, so I can work out how the distance that they've traveled in the 60 seconds. So delta x for A is going to equal 17.89 times 60 seconds, and that's equal to 1073.4 meters. Then the delta x for B is going to equal 113.33 times 60, which is equal to 6,800 meters. Then the distance d between them is going to be the sum of these two values, which is going to be 7873.4 meters. Let's take a look at question 7, electrostatics. The diagram below shows a metal sphere A on an insulated stand in a vacuum. 4.625 times 10 to the 10 electrons are removed from sphere A. Point P is 90 centimeters away from sphere A. Question 7.2, explain why sphere A is placed on an insulated stand. That's because we don't want any charges to be lost. Question 7.3, calculate the charge on sphere A. We can use the quantization of charge formula. Q is equal to N times QE. It's lost 4.625 times 10 to the 10 electrons multiplied by the charge of an electron, 1.6 times 10 to the negative 19. That's going to give us an answer of 7.4 times 10 to the negative 9. Yep, times 10 to the negative 9 coulombs. Question 7.4, calculate the magnitude of the electric field at point P due to sphere A. So electric field E is equal to KQ over R squared. So 9 times 10 to the power 9 multiplied by 7.4 times 10 to the negative 9 divided by 0.9 all squared. Remember that the centimeters need to be converted to meters. That gives us 82.22 Newton coulombs. Question 7.5. So another sphere B carrying a charge of minus 5 nanocoulombs is placed at point P. So we're placing a sphere here, B. Calculate how far from point P sphere B should be placed to decrease the net electrostatic force between the two spheres by 15%. So what's 6 marks? So we're going to have to do multiple calculations. Let's first calculate the electrostatic force when B is at P. So let's just say F is equal to K Q1 Q2 over R squared. So 9 times 10 to the 9, and then 7.4 times 10 to the negative 9, and then 5 times 10 to the negative 9, all over 0.9 all squared. That gives us 4.11 times 10 to the negative 7 newtons. Now, the net electrostatic force is going to decrease by 15%. So that means there's going to be 85% left. So I'm going to say 85, so 0.85 times this force, so 4.11 times 10 to the negative 7, and that's going to equal 3.49 times 10 to the negative 7 newtons. This is the force that we are dealing with, and we want to figure out what should the distance be if the force is going to be that. So we're going to say F nu is going to equal K Q1 Q2 over R squared. The new force is 3.49 times 10 to the negative 7. That's equal to 9 times 10 to the power 9. 7.4 times 10 to the negative 9. 5 times 10 to the negative 9 divided by R squared. So R is going to equal 0.976 meters. So this is where it should be. But the question is asking how far away from point P should it be? So we're going to say that the distance is going to equal 0.976 minus point P was 0.9 meters originally away. So that's going to equal 0.076 meters from point P. Let's take a look at question number 8. In the circuit diagram below, the battery has an EMF of 10 and an unknown internal resistance R. V1 is connected across the open switch and V2 is connected across the battery. Resistance of the ammeter and stuff can be ignored. Question 8.2, determine the reading on V1 and then V2. So the switch is open, so no current is flowing through the circuit. So V1 and V2 are connected technically across the terminals of the battery. So V1 and V2 are both going to read 10 volts each. The switch S is now closed. The reading on V2 drops by 2.5. Now what's going to be the reading on V2? Well, if V2 was reading 10 and it drops by 2.5, V2 is now going to read 7.5 volts. Question 8.3.2, calculate the reading on the ammeter. So the ammeter here is reading the total current in the circuit. So what we can do is we can calculate the total resistance. So we'll start with the parallel combination. We'll say R parallel is equal to product divided by sum. We're going to have 6 times 3 divided by 6 plus 3, which is equal to 2. That means R total for the external circuit is going to be 2 plus the 1 that's in series, which is equal to 3. Now we can calculate the current. So the current total is going to equal the total voltage for the external circuit, so V external, divided by R external. So the voltage for the external circuit is 7.5 divided by the resistance for the external circuit is 3. So that's going to equal 2.5 amperes. Of course, you can use the EMF formula, but it's not necessary. This is fine. This gets you the answer. Question 8.3.3, calculate the internal resistance of the battery. So 8.3.3, the 2.5 volts that dropped is actually known as the lost volts. So what we can do now is we can say that lost volts is going to equal the total current times the internal resistance. So 2.5 is equal to total current is 2.5 multiplied by R. So that means R is equal to 1 ohm. Question 8.4, how will the magnitude of the current passing through the 6 ohm resistor compare to that of the 3 ohm resistor? Now the 3 ohm and the 6 ohm are in parallel, and remember that the current is going to split. But also equally as important is that we must remember that current takes the path of least resistance. So the 3 ohm resistor has a lower resistance, and so more current is going to go through the 3 ohm resistor. So the question is asking, how will the magnitude of the current passing through the 6 ohm resistor compare to the 3 ohm? The 6 ohm will have a lower current. As a matter of fact, because 6 is double 3, we can say that the current going through the 6 ohm resistor is going to be half the current going through the 3 ohm. Question 9 reads, the diagram below shows a horizontal rectangular coil ABCD placed between magnets. The coil has a current when an upward force F is applied to AB of the coil. So that sentence is giving us a clue, and it's actually telling us that this is a generator because you are experiencing a current when a force is being applied. Question 9.1.1, explain why there is a current induced in the segment AB. And that's because of there's a change in the magnetic flux. So change in magnetic flux. Question 9.1.2, determine the direction of the current in AB. Write down A to B or B to A and explain your answer. Now, because we've figured out that this is going to be a generator, we need to use our right hand rule. Now, our index finger is going to be pointing from left to right. Our thumb is going to be pointing up, and that means that our middle finger is going to be pointing from A to B. In other words, it's going to be pointing away from us. So if I could just sketch this out, my thumb is pointing like this, my index finger is pointing there, and my middle finger is pointing in that direction. It's not the best image, but I think it kind of explains it. You got to do it to actually figure it out. So the answer is going to be A to B. And why or how do we know this? It's the right hand rule. A change is made to the device to operate as a DC motor. Name the part of the component that makes it possible for the machine to operate as a DC motor. So this is going to be a split ring commutator. It's actually advisable to write the full thing, not just write split ring or commutator, just write the whole thing, split ring commutator. Question 9.1.4, name one change that can be made in the diagram above to produce a greater turning effect on ABCD. So there's three things you could do. They ask for one. One, you could use a stronger magnet. If you increase the strength of the magnet, you're going to increase the rotation. So stronger magnet, right? The second thing you could do is you could increase, now if it's working like a motor as they're saying here, you could increase the number of cells. So you could increase the voltage or increase the EMF, any number of things. And the last one, you could increase the current. Question 9.2, this is actually a nice question. It says a 120 watt television and two 50 watt tungsten lights are connected to a 230 volt AC supply that operates for only 12 hours a day when S1 and S2 are closed. How long should S1 be open in a day while S2 is closed in order to save 36 Rand weekly, 7 days? The cost of electricity is 9 Rand per kilowatt hour. Now, I haven't seen a question like this in ages, and the trick here is we actually don't need to use any RMS equations. We don't have to use any power equations. The only thing, of course, you could do that, but the easier way, the way that I'm going to approach it, is only focusing on the TV itself. So as the TV is functioning now in its current state, it's operating for 12 hours a day. So I want to work out the cost of this television. So the cost is equal to the power times the rate times the time. So the power is 120 watts. 120 watts is 0.12 kilowatts. Remember, we need to convert that to kilowatts. The rate is 9 rand and then multiply by the time. So we are using it for 12 hours a day, but we are using it for 7 days. So in a week. So let's multiply. So 12 times 7. And that's going to give us 90 rand and 72 cents per week only for the TV. Right? Now we want to bring this cost down by 36 rand. So we want the new cost to be 90 rand and 72 cents minus the saving, minus the 36. And that's going to equal 54 rand and 72 cents. Now that we have the new cost, we can calculate the time. We can say 54.72 is equal to 0.12 times 9 times t. T is then equal to 50.67 hours per week. Now, what is the difference? The difference is 12 times 7 minus 50.67, and that's equal to 33.33 hours a week that the TV needs to be off for. So that the TV should be off. Now, how many hours is that a day? We'll say 33.33 divided by 7, and that's equal to 4.76 hours a day. Now let's take a look at question 10, the last question in the paper. In the diagram below, an incident light is shown on the metal surface photocell. A learner uses the photocell to determine the photoelectrons emitted. The total output power of the electromagnetic radiation waves from the surface is 3.2 times 10 to the 27 joules per second. The wavelength of the incident light is 5.2 times 10 to the minus 7 meters. Question 10.2, determine the number of photons emitted per second from the metal surface. Now, we have the incident light. So the wavelength of the incident light is equal to 5.2 times 10 to the minus 7. So because we know this, we can calculate the energy of the light. The energy is going to equal Hc divided by lambda. Now, 6.63 times 10 to the minus 34 multiplied by 3 times 10 to the power 8 divided by the wavelength 5.2 times 10 to the minus 7, and that's equal to 3.825 times 10 to the minus 19 joules, and this is per photon. Right? Now, if we want to calculate the number of photons, we're going to say that the number of photons is going to equal this value. This is telling us the total amount of energy per second. So, in other words, it's the power. The total energy per second, the power. So we'll say 3.2 times 10 to the 27 divided by 3.825 times 10 to the minus 19. And that's going to give us 8.4 times 10 to the 45 photons per second. In case you're not sure how this works out to photons per second, let me show you with the units. So this is j dot s to the power minus 1, and that is j. The j cancels and you're left with s to the power minus 1, which is essentially per second. Now let's take a look at 10.3. How will the maximum kinetic energy of the photoelectrons be affected when incident light of a shorter wavelength is used? So if you decrease the wavelength, you are increasing the frequency, and if you increase the frequency, you are increasing the kinetic energy. Question 10.3.2, a metal with a higher work function is used. Remember, E is equal to W naught plus EK. If there is a higher work function, there's going to be less kinetic energy, since we are assuming that the energy of the incident light is going to be the same. So that answer is going to be decrease. So let me just write it out here. Increase, decrease. And then 10.3.3, incident light of greater intensity is used. Intensity has no effect on the kinetic energy. All it does is affects the number of photoelectrons. And that's the whole paper. However, for those of you who are or were thinking about the work function of this metal, because they didn't speak about the work function. So that's one of the things that was raised in the discussion, was when we are calculating the energy here, right, we aren't taking into account the work function. So there is an argument to be made that perhaps this question has an error in it, but we've solved what we could with the information that we have. And we leave the rest for those people who are setting the memos and so on. And that's it. Guys, thanks so much for watching. If you stuck around, don't forget to leave a like, share, and subscribe for more. I'll see you in the next one. Bye.